3rd edition. Electricians. Guide to Conduit Bending. 3rd edition. Electricians. Guide to Conduit Bending. Richard A. Cox. Journeyman electrician, retired IBEW Local 73. Retired Chairman Electrical Robotic Department. Spokane Community College. AAS Occupational Education. BS University of the State of New York. MS Eastern Washington University. Co. www.coxco.net. 1-800-257-0941. 3rd edition. Electricians. Guide to Conduit Bending. Copyright L1J 2012, 1982, 1976. Penned O'Reilly Publications and COXCO. 11501 Highland Road, 9 Mile Falls, Washington, 99026. www.coxco.net. Library of Congress Catalog Card Number 8281759. All rights reserved. Reproduction or use, without express permission, of editorial or pictorial content, in any manner, is prohibited. No patent liability is assumed with respect to the use of the information contained herein. While every precaution has been taken in the preparation of this book, the author and publisher assumes no responsibility for errors or omissions. Neither is any liability assumed for damages resulting from interpretation or application of the information contained herein in the execution of electrical work completed by any company or individual. Special thanks to the following companies who furnished photographs, diagrams and/or technical data. Enerpac, Milwaukee, Wisconsin. Greenlee Textron Inc., South Haven, Mississippi. Allied Tube and Conduit Corp. Harvey, Ill. Gardner Benders, Milwaukee, Wisconsin. Graphics, Inland Northwest Industrial Training. Newman Lake, W.A. Lindsay, Hayesville, N.C. 2/13. Printed and bound in the United States of America. National Color Graphics, Inc. Spokane, W.A. 9920. For my wife and best friend, Patricia. Introduction. The purpose of this text is to assist the reader, apprentice or journeyman with developing the techniques required to accurately and efficiently bend conduit. Exposed conduit work is one area of an electrician's job that puts their skill on display. Exposed conduit is there for all to see and directly reflect on the knowledge and workmanship of the installer. With these thoughts in mind, it then will benefit all electricians to learn one of several methods of bending conduit that will assure accurate and precision bent conduit. Conduit that you can step back and look at with pride in the knowledge that it was bent right the first time. The formula methods that the text will deal with at first will seem slow and time-consuming, but as you learn the method and become confident with the bender and your own abilities, it will be quicker and less time-consuming than any other. About methods in use by many electricians in the field today. Some explanations of mathematical or trigonometric functions have been oversimplified so the reader may understand the principles and relationships without an extensive math background. Terms and terminology used in the text, as with any trade, may be regional. A wow in Chicago, Illinois, may be a hoop-de-doo in Butte, Montana. For this reason, a complete glossary of terms is included with definitions. The reader, therefore, need only pick the definition that fits the term used in your area and the text will be understandable. The text will lead you through the steps of procedure for formulated bending, and then let you apply what you have read with sample problems. The correct answers for each problem can be found at the back of the book. It is intended that these sample problems will enable the reader to gain confidence in the system and themselves. For the best understanding of the material, read the chapters in order. Reference is made back to preceding chapters as to the methods and techniques, and continuity will be lost if you attempt to skip around. It should be stated that with few exceptions, the methods and procedures outlined in this text are not original with the author, but a culmination of ideas, techniques, and methods of many fine electricians from throughout the United States and Canada, men and women that he had the pleasure of working with and sharing ideas on conduit bending. Although I would like to give individual credit, the list is too innumerable and I will simply say, thank you, to those involved. Richard A. Cox. It is difficult to climb the ladder of success with your hands in your pockets. Author unknown. Table of Contents. Chapter 1. Basic Trigonometry I. Right Triangles I. Pythagorean Theorem -9. Chapter 2. Electrical Metallic Conduit 10. Bending EMTEO Hand Benders 2. Chapter 3. 90-degree Bends 16. Finding Bender Take Up 16. Chapter 4. Back-to-back 90 degrees Bends 20. Chapter 5. Kicks 23. Chapter 6. Offsets 25. Offset Multipliers 29. Chapter 7. Predetermining offset location 34. Predetermining offset's location method number 1 to 34. 45 degrees offset constant table 36 EMT offset constant table -40. Offset multiplier table -41 offset location multiplier table 42. Predetermining offset's location method number 2 to 43. Shrink value table -44. Chapter 8. Parallel offsets 48. Chapter 9. 4 bend saddles 52. Predeterminingsaddlelocation 53. Method number 1 for predetermining saddle location -54. Method number 2 for predetermining saddle location -55. Chapter 10. 3 bend saddles 58. Predetermining saddle location using shrink -62. Chapter 11. Bending around a corner 65. Round obstruction 65 square obstruction 66. Rectangular obstruction -67. Predetermining bend marks round obstructions 68. Predetermining bend marks square obstructions -69. Predetermining bend marks rectangular obstruction -70. Chapter 12. Rigid metal conduit 71. Types of rigid conduit benders -73. Manually bending rigid using a Hickey -73. Mechanical benders -75. Electrical benders -75. Hydraulic benders -76. Chapter 13. Bending with a mechanical style bender 77. Amount of travel method -79. Finding total pipe length required -81. Push through bending -89. Locating bend mark from the opposite end of the pipe -90. Predetermining saddle location -100. 3 bend saddles using Chicago style benders IOI. General Chicago bending tips IO3. Chapter 14. Hydraulic benders 105. Bending tips for aluminum pipe I08. Chapter 15. Layout for segment bending 109. Chapter 16. Segment bending techniques 117. Bend degree protractor I17. Magnetic angle finder I18. Amount of travel method I19. Number of pumps method L2L. Segment offsets I24. Segment saddles -126. Chapter 17. Concentric bending 128. Concentric 90 degrees bends L28. Concentric offsets -131. 1. Shot parallel offsets I33. Chapter 18. Intermediate metal conduit, IMC, 134. Bending IMC 135. Chapter 19. Rigid non-metallic conduit, RNC, 137. Bending PYC I37. Chapter 20. Finding an unknown radius 141. Alternate methods -143. Chapter 21. Bending pipe with larger than normal radius 145. Tables and charts 149. Conduit trade sizes and dimensions 152. Conduit spacing chart 155. Glossary I56. Answers to problems 159. Other books and tools 165. Basic trigonometry 1. A very basic understanding of trigonometry is needed to fully understand and appreciate formula conduit bending. Once the basic relationships of the right triangle are understood, the serious student of conduit bending can then fully understand how and why the methods work, and will be able to develop their own formulas or tricks to make the job easier. Right triangles. Right triangles will have one angle that is 90 degrees and two other angles that when added together will equal 90 degrees, for a total of 180 degrees for the three angles. The 90 degrees angle is called a right angle, while the other two angles off less than 90 degrees are called acute angles as shown in figure 1.1. It is important to identify the angles of a right triangle. The 90 degrees angle is identified with a square as shown in figure 1 to 2. Off to two acute angles one must be identified so we can use it as a reference when naming the sides of the right triangle. The reference angle in figure 1 to 2 is called angle theta. Angle theta is identified by using the Greek letter E, as shown in figure 1 to 2. Figure 1 to 2. Angle theta. The side opposite angle theta, E, is called the opposite side, as shown in figure 1 to 3. Figure 1 to 3. Opposite side. The side next to, or adjacent to, angle E is called the adjacent side as shown in figure 1 to 4. Figure 1 to 4. Adjacent side. The remaining side of the right triangle, which is opposite the right angle and touches both acute angles, is called the hypotenuse, as shown in figure 1 to 5. Figure 1 to 5. Mathematicians have been impressing laymen with strange-sounding terms for a long time. Even if the terms are strange sounding, they should not cause panic. 3 such alien terms are sine, cosine, and tangent. These terms quite simply are numerical values, constants for given angles of a right triangle. These numerical values are found in the trigonometric function table located in back of the book. These terms, sine, cosine, and tangent, give us the ratio between any two sides of a right triangle. The ratios may be stated in formulas. Sine of angle 0 equals 0. H. Cosine of angle 0 equals A. H. O. Tangent of angle, J equals A. O equals opposite side. H equals hypotenuse. A equals adjacent side. By using the formulas, we can find any side of a right triangle, or the unknown value of angle theta. As with any formula of this type, two values must be known to find the third or unknown value. Using the formula sine equals H, O as an example, if the sine of the angle is known, and the hypotenuse is known, only the opposite side and adjacent sides remain to be found. To find the opposite side, the original formula sine equals H, O would have to be transposed algebraically. By placing formulas in so-called magic circles, they are easier to handle and transposition is not necessary, greatly simplifying the math. Figure 1-6 shows the three formulas, sine, cosine, and tangent converted into magic circles. Figure 1-6. Sine equals O, H. Cosine equals A, H. Tangent equals O, A. In a magic circle, letters separated by a vertical line I are multiplied, while letters that are separated by a horizontal line are divided. Figure 1-7. Example. If we know the hypotenuse and wanted to find the opposite side, we can use the sine formula shown in figure 1-7. Simply place your forefinger over the unknown value A, opposite. The vertical line between the S and the H in the circle tells us to multiply the sine of the angle theta, by the value of the hypotenuse to find the opposite side. Had we known the measurements of hypotenuse and the opposite side and wanted to find the sine of the angle, we would cover the unknown sine, and the circle tells us to divide the opposite side by the hypotenuse to find the sine of angle theta, as shown in figure 1-8. Figure 1-8. This is a very basic presentation of trigonometric, trig, functions, but should be adequate enough to understand the relationship that exists between the opposite side, 0, the adjacent side, A, the hypotenuse, H, and angle theta, B. Reference will be made throughout the text to these relationships, and if you can understand the relationships, you will be able to develop your own formulas. Trig functions will also be used to determine where bends are to be made, and also to determine the degree of bend. Let's try some examples to see how this works. Example. Assuming we want to bend a piece of conduit at 24, and want it to raise 8. What degree of bend will be required? 1. First draw the problem, as shown in figure 1-9. 2. Look at it now as a right triangle, redraw and label the hypotenuse and opposite sides, as shown in figure 1-10. 3. Select a formula that has the two known values hypotenuse and opposite side. The sine formula, as shown in figure 1-1I meets our needs. 4. Replace letters with the measurements from the problem and divide as indicated in the formula. Sine equals tilde sine equals 0.33324. 5. Using the partial trigonometric table shown in table 1-12, we see that the closest angle to a sine of 0.333 is 19 degrees, so we can say that the angle will be equals 19 degrees. Partial trigonometric table. The approximate symbol equals will be used in the text to indicate an answer that is close to, or is an approximate number or value. We could now place the center of a bender shoe on the 24 inches mark on the pipe, and using a protractor level or other device bend the conduit to 19 degrees, knowing ahead of time that we would get the desired rise and length. In reality, we would not go to all this trouble for such a simple bend, but did so only to try out the formulas. This was not all wasted time and effort, however, for this is the procedure to determine rate of rise of a conduit. The ratio of the sides of the triangle, to a given angle theta, remains constant, even if the size of the triangle increases, as shown in figure 1-13. Notice that if the hypotenuse doubles in length from 24 inches to 48 inches, the dimension of the opposite side also doubles from 8 inches to 16 inches, but the angle of theta remains unchanged. Sine equals O, H. Sine equals 16/48. Sine equals 0.333. Or equals 19 degrees. If the hypotenuse is tripled in length, the opposite side also triples, yet angle theta, 0, remains the same. Sine equals O, H. Sine equals 24/70. Sine equals 0.333. Or equals 19 degrees. The ratio between the hypotenuse and the opposite side will hold true no matter how large the triangle becomes. So in a practical sense, we could say that if we bend our conduit 19 degrees at 24, it will rise 8 inches, or the rate of rise is 4 inches per foot of length. If a 10 feet, 120, section of conduit was added, we know the rise would increase 4 inches times 10, or 40. Add this amount to the original 8 inches rise for a total of 48 inches, as shown in figure 1 to 14. To prove our figures and check the rise again, let's use the formula. Sine equals OH. We know the angle of the bend is 19 degrees and that the hypotenuse is now 144 inches, 24, plus 120 inches for the 10 feet piece of conduit that was added. The unknown then would be the opposite side, which will be the rise of the conduit. Cover the opposite side of the magic circle as shown in figure 1 to 15. The circle tells us to multiply the sine of the angle, 0.333, by the length of the hypotenuse, 144. O equals 0.333 times 144. O equals 47.952 asterisk or equals 48. Asterisk. The small error is caused by selecting the closest degree for a sine of 0.333 at the beginning of the problem. But this is certainly close enough as we can only expect accuracy in conduit bending to within 1/8, or 0.12500. Example. A pipe must be bent at 44, and have a rise of 13. What angle of bend will be required? Draw the problem and label it as a right triangle, as shown in figure 1 to 16. Use the formula S equals OH. Substitute values S equals 13/44. Solve. Sine equals 0.2954. From table 1 to 17, the closest angle to a sine of 0.2954 is 17 degrees, which has a sine of 0.2924. The conduit is then bent to 17 degrees to get a rise of 13 inches. Table 1:17 Partial trigonometric table. Problems. 1. How far will a pipe rise if it is bent 30 degrees at 48? What is the rise per foot? 2. An electrician has bent a piece of conduit, as shown in figure 1 to 18. What is the angle of bend A? 3. A guy wire 100 feet long is attached at the top of a pole and secured to the ground 40 feet from the base of the pole as shown in figure 1 to 19. A. What angle does the wire make with the ground? B. How tall is the pole? Pythagorean theorem. Another method of solving problems dealing with right triangles that does not require you to know angle theta is called Pythagorean theorem and was developed over 2,500 years ago. Pythagoras was a Greek scholar who found that the square areas of two legs, or sides of a right triangle, adjacent and opposite, when added together, exactly equaled the square area of the hypotenuse, as shown in figure 1 to 20. The theorem, simply stated, gives us the formula a squared plus o squared plus h squared. By transposing the formula we get the following three formulas. H equals square root a squared plus o squared. O equals square root h squared minus a squared. A equals square root h squared minus o squared. Example. To find the hypotenuse of a right triangle, the h formula requires you to find the square root of a squared plus o squared. While it would be very difficult to solve this formula longhand, it can be done quickly using a pocket calculator. H equals square root a squared plus o squared. H equals 16 plus 9. H equals square root 25. H equals 5. On your calculator the keystrokes would be electrical metallic tubing 2. Electrical metallic tubing, or EMT, is also referred to as steel tube or thin wall. Article 358 of the National Electrical Code 7 covers the installation and use of EMT. EMT is a listed metallic tubing approved for the installation of electrical conductors when joined together with listed fittings. EMT is relatively easy to bend, cut, and ream, and because it is not threaded, all connectors and couplings are of the threadless type. Standard trade sizes for EMT are 12, 3/4, I, 1 foot, 4, 1 foot 12 inches, 2, 2 feet 12, 3, and 4 inches and are manufactured in standard I0 lengths. Bending qualities will be affected by the ductility asterisk, uniformity, and surface treatment of the conduit, and these qualities will vary with each manufacturer. Ductility is the ability of a material to be bent or formed. Bending EMT. EMT may be bent with hand benders, Chicago style mechanical benders, electric and hydraulic benders. Hand benders are usually restricted to 12% I and 1 foot 4 conduit sizes. Over IV would require physical strength not possessed by most electricians. Chicago style mechanical benders vary with the manufacturer, but most will bend up to 2 inches EMT. Electric and hydraulic benders are available that will bend Y through 4 inches EMT. Only hand bending techniques will be discussed for EMT. Chicago style mechanical, electric, and hydraulic bending methods are covered under rigid conduit, and the techniques as outlined there will also apply to EMT. Hand benders. All hand benders will have a curved shoe that will be used to form the conduit, a hook that will hold the pipe at the front of the shoe, and a hack or foot piece for applying pressure to keep the pipe in the shoe while the pipe is being bent. Figure 2I shows a Benfield bender head. Hand benders are offered by many manufacturers and are basically of 2 types. Benders that will have bent a 45 degrees bend when the handle is vertical or perpendicular to the work surface, floor, as shown in figure 2-2, and benders that have bent a 30 degrees bend when the bender handle is vertical as shown in figure 2-3. 30 degrees and 45 degrees bends are used frequently when bending offsets. Offsets will be covered in Chapter 6. The handle of the Gardner bender, as shown in figure 2-2, will be perpendicular, plumb, or vertical to the work surface when a 45 degrees bend has been achieved. The Benfield bender head shown in figure 2-3 has angle indicating marks of 10 degrees, 22 degrees, 30 degrees, 45 degrees and 60 degrees on the side of the bending shoe. When an angle mark is parallel to the work surface, that angle of bend has been achieved. This bender handle will be perpendicular, plumb, or vertical to the work surface when a 30 degrees bend has been achieved. Figure 2-3. Each manufacturer puts marks, arrows, stars, letters, etc. on the bending head to locate or indicate starting points for bending 90 degrees bends, offset bends, center of bend, make adjustment for back-to-back bends, etc. Take the time to read the instructions that come with each bender head. If no literature is available, make some sample bends with scrap pipe to familiarize yourself with the bender and its marks. The time will be well spent, and will pay dividends in time and material saved when the actual bending is started. Benders normally do not come with a handle. The handle is cut from standard size rigid or IMC conduit, and then screwed into the bender head. To save back strain, and to gain mechanical advantage, the top of the bender handle after it has been screwed into the bender head should reach the center of the elbow of the user when stood upright on the floor next to the body, as shown in figure 2-4. The key to accurate bending with a hand bender is constant and heavy foot pressure on the back piece, or foot piece of the bender. Failure to keep constant pressure on the back, foot piece will allow the conduit to rise off the floor and bend outside the bending shoe. Proper body positioning when bending conduit will give added leverage and make the job easier. Figure 2-5 shows the proper stance for initial bending of a 90 degrees bend. Hold this position while pulling the handle back toward the chest with constant heavy foot pressure on the foot piece until the handle is well past vertical. Change body positioning, spacing feet further apart, while still maintaining good pressure on the foot piece. The bend can now be completed by pushing down on the bender handle, as shown in figure 2-6. For hand bending 1 1/4 EMTA 2-step bender like the Greenlee Citrite shown in figure 2-7 will be required. The bender head is available in either an aluminum or iron alloy and features a 2-step oversized foot piece that allows more foot pressure and better control during the 2-step bending process. Many manufacturers indicate that their EMT benders can be used to bend the next smaller sized rigid pipe, i.e. 1-inch EMT bender can also bend 3/4, rigid, 3/4, EMT bender can also bend 1/2, rigid. The author's experience has been that when bending rigid conduit with a bender head made of aluminum, the rigid conduit may distort the bending shoe and ruin the bender. If you want to bend rigid conduit with an EMT bender, use an iron alloy bending head, not an aluminum head. Trying to bend EMA pipe with an aluminum EMT bender will usually break the front hook of the bender. An EMT bender can also be ruined by loaning the bender to an iron worker to bend rebar. It is also important to keep the bending shoe clean, as dirt or buildup on the shoe can cause the bender to kink the pipe. 90-degree bends 3. 90-degree bends are called stubs, or stub-ups. The stub or stub-up length is measured from the back of the completed bend to the end of the pipe, as shown in figure 3-1. The length of pipe left after the stub has been bent is called the leg length. Figure 3-1. The 90 degrees bend is the most frequent bend the electrician will make, and also one of the easiest. To bend stubs to a given dimension, the take-up of the bender being used must be known. Take-up is the distance from the arrow, star, or other mark on the bender, to the back of the completed bend, as shown in figure 3-2. Finding bender take-up. To find the take-up, or to check the take-up printed on the bender, proceed as follows. 1. Measure 6 inches from the end of a scrap piece and place a mark. 2. Place the arrow, star, or other mark on the bender on the 6 inches mark as shown in figure 3-3 and bend a full 90 degrees bend. Accuracy at this point is very important, so check your bend with a level. 3. Measure the overall stub length and deduct 6. The remainder is the take lip for that bender, as shown in figure 3-4. Take up then is the measurement from the arrow to the back of the bend, or by subtracting 6 inches from the overall stub length. If the overall stub length is 11, subtracting 6 inches would give us a take-up value of 5. Once the take-up for a given bender has been found, the take-up value can be used to bend perfect 90 degrees stubs to any stub length you need. Example. We want to bend a 12 inches stub using 1/2 EMT. We have determined that the 1/2 EMT bender we are using has a take-up of 5. All we need to do to bend a 12 inches stub then is to subtract the bender take-up of 5 from the 12 inches stub length, leaving 7. Place a mark 7 inches from the end of the pipe and then place the arrow of the bender on the mark, as shown in figure 3-5. Next make a 90 degrees bend. The result will be a perfect 12 inches stub. In embedded or underground conduit work where accuracy and appearance is not so important, a quick method of bending 90 degrees stubs is by sighting down the back of the bender footpiece. Notice in figure 3-5 that the back of the bending shoe lines up with the 12 inches measurement for the desired stub length. If a 12 inches stub is required, measure 12 inches from the end of the conduit and place your thumb there as a reference. Place the bender shoe on the conduit and sight the back of the bender footpiece. Move the conduit in the bender until the back of the footpiece, back of bender shoe, is lined up with the thumb mark, 12 inches. Set the bender down and bend a 90 degrees stub. This is called an about method and is not accurate enough to be used for exposed conduit runs. Rule. When bending stubs using the take-up method, the bender is always placed on the pipe and the bend is made facing the end of the pipe the measurement was taken from. Tip. Once the length of the stub has been determined, deduct take-up in your head to find the bend mark. Do not mark the pipe. Instead, place the bender on the conduit in the approximate area where the mark should be. Support the conduit in the bender with one hand. Hook the end of a steel tape over the end of the conduit and then slide the bender until the arrow of the bender is on the proper measurement, as shown in figure 3-6. Set the bender down and bend a 90 degrees stub. This eliminates fumbling for a pencil and saves time. To straighten a stub that has been overbent, place bender handle, or any close-fitting pipe, over the stub, as shown in figure 3-7, and push down and away. For larger sizes of EMT, a close-fitting pipe that will fit inside the pipe will also work. This method can be used to remove the whole bend. As part of the bend is removed, move the bender handle further down and continue to remove the bend. Success with this method depends greatly on the ductility of the EMT. The pipe will show that a bend has been removed. This method is okay for buried work, but not for exposed conduit runs.